Hello and welcome to this session on multi-level models and spatially variable area sinks. We'll start off looking at the decision between using a 2D approach or a 3D approach and some guidance around that and some tools and approaches you can use for discerning that. We'll look at how Anaqsim computes vertical leakage, which is basically in accord with Darcy's law. We'll look at the general flow equation when we have the need for SVASs and how that is simulated. And then we'll look at how you set up your SVASs and their basis point spacings and how you can check the accuracy of your SVAS. We're very often faced with a decision to make about whether to use a two-dimensional model or a three-dimensional model. And a 3D model accounts for resistance to flow in all three directions, whereas a 2D only accounts for resistance to flow in two directions, usually the horizontal plane. And this kind of makes sense because of the actual dimensions of many aquifers. They're often only tens of meters in the vertical and hundreds, thousands, maybe even 10,000s of meters horizontal. So if you're looking at a regional scale, 2D often makes sense. The case for 2D isn't just a matter of dimensions when you've got a big contrast between the horizontal and vertical conductivities. If the horizontal is, say, 2 orders of magnitude greater than the vertical, then we have to look at a scaled equivalent isotropic media and think about it that way, which we'll get into. Let's think about 2D versus 3D modeling with a specific example. So here's a vertical cross-section of our problem, which has a partially penetrating well screen near the base of the aquifer here, and a partially penetrating river in the top of the aquifer over here, and we're wondering about modeling the interaction of those two things. So if you just look at the true scale, there's a lot more horizontal distance than vertical distance between these two things. But let's say we have a 10-to-1 horizontal to vertical ratio of conductivities. To get the equivalent isotropic domain in a vertical profile, we would scale the vertical by a square root of that ratio 10 and get a profile that looks like this. And again, we look at typical flow paths in that scaled section, in the equivalent isotropic section, and it looks to be mostly resistance to horizontal flow, not vertical flow, that dominates. So a 2D analysis may be okay there. Then let's take it up to a 100-to-1 horizontal to vertical conductivity ratio and scale it by 10, which is the square root of that ratio. And now you can see that by neglecting the vertical resistance to flow along these paths in the equivalent isotropic domain, we're missing out on a fair amount of the problem. So if you wanted to model this aquifer with that 100-to-1 ratio, you'd probably want to do a three-dimensional analysis, and in Anaqsim that would be a multi-layer model. So this is a good approach. Make a scaled vertical section of your critical flow paths and think about how much horizontal versus vertical resistance there is. Another way to discern 2D versus 3D is if you've got a 3D model, you can look at the head differences between the different layers or levels in your model and see whether they are significant. And this is kind of analysis in hindsight, but let's take a model here that has 3 layers, and we've got a plot of heads along a line, something we generated using the analysis menu, and we've got a pumping well in level 3 and a little bit of drawdown up in level 2 and a little bit in level 1, but the head differences are kind of trivial outside of, say, a 200 meter or 200 foot radius, I don't know what the units are in this model, of the well. So you could conceivably, in this case, use a stack of 3 domains right in the near vicinity of the well, within 100 or a couple hundred units of the well, and then outside that, go back to a single layer and save yourself a lot of computation. And this second bullet here notes that if you're really interested in path lines and travel times, you may want to stick with multiple layers if there's contrasts in hydraulic conductivity that would alter both travel times and path lines. If you have an aquifer system with substantial aquitards that are much lower conductivity than your aquifers, that's usually a clear case for multi-layer modeling. And you can model those aquitards explicitly, like include them as a layer in your model, or you can model them implicitly, not include them, but incorporate the vertical resistance they offer into the vertical conductivity, the K3, in the aquifer that's just above or just below it. And we'll talk about that more in a second here. When the horizontal conductivity of an aquitard is far, far less than the horizontal K of the aquifers that are above and below it, you can model that aquitard implicitly, like you don't include that aquitard layer as a separate layer in your model, but instead you neglect any horizontal flow that would happen in the aquitard, and you do incorporate its vertical resistance to flow by adjusting the K3, the vertical conductivity of either the aquifer just above or just below. And to do that, you can use equations for the equivalent conductivity normal to layers, which I cite my own textbook here, and I believe the equation number is the same in the 3rd edition that came out in 2023. And you'll find a similar equation or the same equation in other groundwater textbooks. As I said, you neglect the horizontal flow in the aquitard. One other consequence, which may argue against doing this, if you're doing a transient model and you have an aquitard that contributes significantly to storage, you don't want to do this because you're cutting out that storage contribution that the aquitard would offer. But if these two approximations are fine, then this could be a very good approach and save you some computation. Let's review the general flow equation in terms of phi, our aquifer discharge potential, and see what impact having a multi-layer and or transient model has. Our general equation is this first one, where the Laplacian, which is the sum of the second derivatives in the x and y directions of our discharge potential, equals these 3 distributed source sink terms on the right. Leakage out the top of our prism, which spans the saturated thickness of the aquifer, leakage out the bottom of it, and then flux into storage if it's a transient model here, this 3rd term. So these are distributed areally, which require an area sink, which we'll talk about soon. And we approximate this general equation in Anaqsim, and in fact this is done in most numerical models as well, using finite difference time steps. So instead of a derivative which applies at a specific instant in time, we approximate that with a finite difference derivative here over a time interval, delta t. That's our time step length. And this is the head change that occurs over that time step length. When we have multiple layers, vertical leakages, and or transient flow, we're going to need a spatially variable area sink, SVAS. And the discharge potential for that spatially variable area sink function has a Laplacian with a finite and spatially variable extraction, this gamma. And the equation for that gamma turns out to be a summation across n basis points, where b sub I is a constant and r sub I is the radial distance from the basis point to the x comma y where we're evaluating this potential. The capital B naught is also a constant. Anaqsim solves for these constants, little bi and large b sub o, by imposing this equation at every basis point. So we perfectly get the extraction we need at each basis point, the sum of the vertical leakages and the flux into storage. In between basis points, we have a smooth distribution of extraction, and this equation is only approximate. So the more basis points you have and the smoother your surface, the better it's going to fit the desired distribution of extraction. And by the way, this is not unlike numerical models where they compute a vertical leakage rate and a storage flux at the center of a cell or at a node, and then they apply that to a broader area in an approximate way. So this is similar in that manner. It's an approximation in between basis points. Here's how Anaqsim computes vertical leakage in multi-level models. It accounts for the vertical resistance to flow between the center lines of the saturated thickness in each domain, and uses the average head to determine the average saturated thickness. So, for example, if we have domain A overlying domain B, A yellow, B blue, the vertical specific discharge from the center line of B to the center line of A is computed using a form of Darcy's law for flow normal to two layers. And we end up with this equation where the vertical specific discharge is a function of the thicknesses d sub A, d sub B, and of the vertical conductivities K3 in the upper half of B and K3 in the lower half of A. And these are inputs in Anaqsim. Since the simulated extraction in Anaqsim is perfect at a basis point, and approximate in between, it follows that denser basis point spacing will give you a more accurate simulation of the distribution of those distributed sources and sinks. And you need more densely placed basis points when you have rapid changes in extraction in the horizontal direction. For example, if you're right close to a pumping well or a partially penetrating well, or close to a feature like a drain or a recharge trench. And you'll also need denser basis point spacings where the vertical resistance to flow is low, relatively lower. And this is somewhat akin to smaller cells or elements in numerical models. And here's an example of a model with an impermeable barrier that's partially penetrating, so it's driving vertical flow down and under the wall and back up on the other side. You'll need denser basis point spacings close to that well, or excuse me, to that wall, to that barrier. And here's a pumping well, and Anaqsim has a routine for placing denser basis points as you approach a well. To help you get in the right ballpark in terms of the basis point spacings you'll need, Anaqsim computes something called the leakage factor for multi-layer models. And this shows up on the left side in the display. And what it does is it factors in the transmissivity, horizontal transmissivity in a domain, its vertical thickness, and the vertical conductivities. And this is one form of this equation, and Anaqsim actually uses a different form that incorporates kind of the upper half of a layer and the lower half of a layer, where we're computing it between the layer we're in and the one above or the one below. But it's similar to this. So you can see that the leakage factor is smaller for a lower transmissivity, lower thickness aquifer, and for one that has a fairly high vertical conductivity. And the basis point spacing that you're going to need is going to be of a similar order of magnitude as the leakage factor. And so it's good to take a look at that and think about starting off anyway with magnitudes of basis point spacings that are similar to the leakage factor. Here's the sequence for placing basis point spacings that's adopted in Anaqsim. First, it goes through the basis points that are associated with a domain SVAS, all the domain SVASs. So you can specify these area sync basis point spacings and the top and bottom conditions by domain or by polygon. So first it goes through all the domain specifications, then it goes to polygons that you may have input, and these, where they overlap a given domain, will overwrite whatever domain assignments had been made in step 1 here. And the SVAS polygon specifications can be nested. So when you have multiple nesting levels of these polygons, the higher nesting level ones will overwrite the lower nesting level ones, as well as any domains that they happen to overlap. So we've talked about this in the previous video. The top and bottom conditions apply at the topmost and bottommost layers that exist at a basis point. So you don't want to specify SVAS domains for any overlapping domains. That would, in those overlapping areas, have multiple inputs that are adding to each other when you don't really intend that. With both the domain and the polygon SVAS, the basis points are placed on a hexagonal grid at the spacing that you specify. Here's an example of basis point spacings in an Anaqsim model, and the illustration here, the basis points are these little green plus symbols. So here is a domain. This blob-shaped polygon is a domain, and we've had input for a domain SVAS over the area of that domain at a spacing of 60. And that leads to all of these basis points, which are on a regular grid. That's a hexagonal grid. We have several polygon SVASs as well, and those are bounded by the cyan colored lines here. We have one at a nesting level 1 with a node spacing of 20, and that's this outermost one here. And the spacing again is a hexagonal grid of basis points inside that, but the spacing is 20 compared to 60 on the outside. Then we have a couple of polygon SVASs nesting level 2. This one right here is inside the one that is nesting level 1, and it sets the spacing to 30, which is coarser than what's outside of it. That's perfectly okay to do, and sometimes I use that, say, in the middle of a pond or something where the vertical leakage isn't going to be changing as rapidly as out near the shorelines, for example. This other one over here is also nesting level 2, but inside of it, the basis point spacing is down to 10, finer than outside, which is 20. And then we have one polygon here, SVAS, that is nesting level 3 inside this 2, which is inside the 1, and that's got a spacing of 5. So this way you can build up and place your basis points just where you need them around key features in your model. Anaqsim has special basis point spacings for wells, and these are very easy to input in the model, and it creates a series of basis points that have radial symmetry and get denser and denser as you approach the well screen. And these start just outside the radius of the well screen and work their way out until the spacing is equivalent to the maximum node spacing that you specify on the input. So what you specify in the input is that maximum node spacing and how many points per circle. In this case, it's 6 points per circle. I think it can be 8 or 10 if you want it to be. And then you can apply this to any number of wells or all the wells in your model. And it's always a good idea to model the basis point spacings around wells this way if you want accurate depiction of vertical leakages and or storage fluxes. Here's an example of well basis point spacings. Again, these green pluses are the basis points. So out here is kind of the ambient background spacing. And here's a pumping well. And from here on in, the basis points are governed by the well basis point spacing, which has a maximum spacing of 25, which is equal to the spacing in the background out here. And these rings of 6 basis points keep getting finer and finer as we approach the well screen inside there. Just to show you the benefit of using well basis points, I've got a model here that has 3 pumping wells in it. One right there, that big heavier green plus sign, and one here and one here. And these two I've used well basis points around, and you can see that the simulated extraction, which is what's being contoured here, is roughly correct. It's a little bit lumpy, but it's awfully good. And this well over here, we didn't use the basis point, the well basis points. And that's very poorly represented in terms of the extraction around that pumping well, whereas it's quite decently represented around these other two, which made use of the well basis points. It's always a good idea when you're using SVAS to check the accuracy of the basis point spacing and how that SVAS is simulating distributed sources and sinks. And you can do that in Anaqsim under the analysis menu, conditions along a line. And here's the form that will pop up if you choose that, and you want to select extraction. And here's the line coordinates that you can digitize and paste in here. And it will generate plots for all the model levels you selected. So for a given level, you'll get 2 curves. The modeled extraction, the gamma that the SVASs produce, and you'll also get a extraction computed based on head differences. So the leakage out the top and bottom would be computed based on the heads in the layer you're in and the one above it for L sub t, and the vertical conductivities in between, and L sub b is computed similarly but with the layer below. And this storage term is computed using a finite difference, head at the current time step minus head at the previous time step divided by the duration of the time step. So the second curve is computed this way with head differences, and these two are going to be exactly the same at every basis point, but what you like to see is not much daylight between these 2 curves. This desired distribution is being approximated well by the simulated extraction. Let's look at an example 3-level model in Anaqsim, and we've got a pond that I'm outlining here that has as a top condition head-dependent flux up out of the top layer of the model into the pond. We have a partially penetrating well near it that is screened down in level 3 at the bottom. And we have recharge coming in everywhere around the outside of the pond, and we have a couple of river elements coming in and going out of the pond. So we have basis point spacings. This is by domain out here, and then these cyan colored things are polygon SVASs, and here in the middle of the pond that made it less dense than near the shores. And I've had another polygon that makes it quite dense near the well, and then well spacings right at the well. So if we were to check the effectiveness and accuracy of the SVAS and basis points for this profile AA, we end up with a plot that looks like this. Let's look at level 3, which is where the well is screened, and you see a spike like this to negative extraction, and that's because it's not losing leakage out the top, it's gaining it in the top from levels above, coming down to feed the well, and that's why we get this big spike in negative extraction. The opposite is the case in level 2. That one's losing a lot of flow, leakage out its bottom, going down to the well in level 3. And then in level 1, we have interesting interactions around the shorelines of the pond. So at this end of things, we have outside the pond here a negative extraction, which is the recharge rate coming in the top, not going out, so it's negative. And then once we get inside the pond, we cross through, there's a separate domain that is in existence under the pond here. We get an abrupt change in extraction to a high positive extraction, and that's the leakage out of the pond near the shoreline, out of the uppermost domain into the pond near the shoreline, and that decays as you approach the middle of the pond. At the other shoreline here, we're near the well, and the pond is actually losing water to the upper layer and feeding the upper layer of the aquifer because there's downward gradients induced by the pumping well. So we have ideally very good correlation between the pair of curves in each of the levels, and we do. You can't actually see significant daylight between the pairs of curves. So we're doing a very nice job of approximating the desired distribution of vertical leakages and storage fluxes here with the basis point spacings we have.